interesting. But I think that thinking and speaking clearly about any one of these topics can be challenging, whether it's physics or philosophy or theology. And so thinking and speaking about the intersection of all three has special difficulties, right? So how I plan to approach this talk is I'd like to talk a little bit about the work that I do in my research laboratory, that's in the physics of fluids. And I want to do this for a couple of reasons. First of all, because I really enjoy talking about the work I do in my laboratory. And I want to give you a sense of kind of what's involved in that. And secondly, and this is maybe the broader issue, is that I really think that when one asks careful scientific questions, one is drawn pretty quickly into deeper philosophical and theological issues. And I think when this inevitably happens, the scientist really has a couple of options, right? The scientist can either say, well, I'm not going to touch that. Those kind of problems are either uninteresting or insoluble, perhaps. And the other approach that one can take is to say, this is an interesting question, and I'm going to try to approach this to the best of my ability with the goal of increasing my understanding, right? So maybe I should say at the outset, what I'm not trying to do here is I am not trying to argue that Christian doctrine can in some way be derived in some deductive sense from doing laboratory experiments. That's not my claim here, and in fact I don't think you can do that with any kind of theological system. My claim is a little bit more modest than that, but I hope it's still a little bit provocative, and it is that when you, as I mentioned a moment ago, when you do careful research, and this isn't just for physics, but I think in a lot of different areas, you, after a few questions, you're getting to philosophical and ultimately theological kinds of questions. And when you start addressing these sorts of questions, this can provide an avenue for exploring some of the tenets of different world systems, and in particular, the Christian faith. So that's sort of the roadmap of where I'm going with this. So maybe to give you a sense of a couple of examples of how this sort of thing happens, how science and philosophy kind of overlap a little bit. So I have a picture here of Isaac Newton. Probably many of you recognize, maybe you recognize this picture of Isaac Newton. It's actually not a picture, it's a painting, right? But Isaac Newton, as you probably know, was a mathematician and a philosopher and a scientist back in the 17th century. And he was known for many things, but one of them is for the development of a mathematical method called calculus. And some of you have probably heard of calculus, some of you may be studying calculus right now at the university, or some of you may have studied it in the past. And what calculus essentially does, among other things, is it provides a way of summing up or adding an enormous number, or perhaps an infinite number, of very tiny quantities. And why is this important? Why is that interesting? Well, it arises in the study of motion. So since ancient times, people have been interested in understanding how things move and why things move in the way that they do. And there are a number of puzzles that arise in understanding kind of the philosophy of motion, right? So I have up here, I have a picture, and I'm referring to Zeno's paradox. Zeno was an ancient Greek philosopher, and he brought up some paradoxes relating to the science of motion. And one of them, I'm going to kind of put this in more modern terms. I'm not going to use his exact example, but I think you'll get a sense of what I'm talking about. He argued that, let's suppose that you were hungry and you wanted to eat a sandwich, and that sandwich is in the refrigerator on the other side of the room. And so in order to get to that sandwich, you need to basically go through a point that lies midway between yourself and the refrigerator, right? So you get to that point midway between yourself and the refrigerator, and then you have to pass again through another point that lies midway between yourself and the refrigerator. And then once again, you have to pass through another point that lies between yourself and the refrigerator, and that goes on and on and on. And in fact, Zeno argued, there are an infinite number of points through which you must travel on the way to get to this refrigerator to get your sandwich. And here's the crux of the argument, is that it is impossible to pass through an infinite number of points in any amount of time. And so, whether that time be 10 minutes or 10 days or 10,000 years, so in the end you will never get to the refrigerator and you will starve to death, right? Now, of course that's preposterous, right? Like, we've all gone to the refrigerator, we've all gotten a sandwich out of the refrigerator, so there must be something wrong with this kind of argument, but what exactly is wrong with this argument. Now, if you study calculus, you'll learn ways to do this. I'm not going to try to explain in detail how one can do this, but the important point is that Newton's calculus provided a way for summing up or adding an infinite number of infinitesimally small quantities. So here you have a situation where a mathematician, a scientist, was approaching a philosophical problem, or a problem that was raised in a philosophical context. And sometimes this works the other way. So sometimes scientific questions raise deeper philosophical issues. And this happened with Newton as well. So Newton is known for developing a universal law of gravitation. So some of you may have heard of Newton's universal law of gravitation. What it basically claims is that every object in the universe attracts every other object with kind of a gravitational interaction, right? So the Earth and the Sun are attracted to one another. In fact, that's what keeps Earth in its orbit around the Sun, is this force of gravity. So how does this scientific question raise deeper philosophical issues? Well, I want to talk a little bit about kind of the history of this topic, of why it is that objects go around the Sun. So since ancient times, people have been interested in why it is that the objects go around the Sun. Well, it wasn't actually phrased that way in ancient times. In ancient times, people were looking at the Sun, the Moon, the stars, the planets. Every day they were rising in the east, traveling through the sky. I don't know which way is east here. Okay, so rising in the east, going overhead, and setting in the west. This had been happening day after day, year after year, for as long as anyone had cared to observe. And so the question is, why do the planets seem to go around the Earth in the way they do? Why does the Sun seem to go around the Earth in the way it does? And one of the primary theories that people came up with, this is a theory that was prevalent for 1,000 years, and this is the idea that the planets and the Sun and the Moon are attached to this kind of celestial gearwork. So imagine like invisible gears filling the skies, they would call them the heavens, and the Sun, the Moon, and the stars were attached to this gearwork, and that was kind of going around the Earth and carrying them around day after day, right? So this is sort of the image in the upper right diagram here. You have a picture of the Earth, and you have these kind of orbits of these spheres that are going around the Earth, carrying the planets around on them. And this might sound a little bit strange, but the idea here is that if the planets and the Sun and the Moon are going around the Earth, it must have a cause, right? And that cause must be some kind of mechanical motion. The planets are kind of riding on these gears. That's the idea behind it, which seemed like a reasonable thing, right? This idea was dominant, like I said, for about 1,000 years. At the time of Copernicus, this is in 1543, he wrote a book called On the Revolutions of the Heavenly Spheres. And in this book, what he basically did is argue, well, we got it kind of wrong, right? So he said it's not really the Earth that's at the center of the universe. Rather, it's the Sun that's at the center of the universe. But the important thing that I'd like to point out is that he didn't really question the existence of this kind of celestial gearwork. In fact, that's why he called his book On the Revolutions of the Heavenly Spheres. He still believed that there were these spheres to which the planets and so on were attached and going around the Earth, right? So he wasn't, his theory was very conservative in that sense. He was kind of maintaining this idea that had existed beforehand, but just kind of reorganizing the gears a little bit, right? So he's being conservative but changing one small thing about it. After the work of, so there's some scientists like Kepler and Brahe who kind of called this into question, but over the next few years. But after the idea of this kind of celestial gear work fell out of favor, it was replaced by another scientific theory, and this was a theory that a man named Descartes came up with. Some of you may have heard of Descartes. He's a philosopher. He's famous for saying, "I think, therefore I am." That's sort of, or some of you may have come across him. He's also the one after whom the Cartesian coordinate system is named. And his idea was, well, this gearwork doesn't make sense. Well, I think instead what's going on is all of the skies, the heavens, the region around the Sun is filled with this fluid. And it was called ether at the time. And he wrote a book called The World. Okay, and I have a diagram down here. There's actually a page from his book called The World. And this is supposed to picture, catch anything here. So the sun is right here, and you've got these kind of swirling motion of this fluid going around the sun. And the idea was that, if you have like a rubber ducky in your bathtub and you pull the drain, the rubber ducky kind of swirls around the drain like this, and that's what keeps it in motion, right? So that's how he conceived of the planets going around the sun. They were kind of caught in this whirlwind of this invisible fluid that was pushing them around the sun. And that's sort of an artist's depiction of this view of Descartes in this lower diagram, right? Now, why am I bringing this stuff up? Well, because in both of these theories, the main idea was that in order for something to move, there must be something with which it is in contact, right? So in the gear theory, you've got the planets attached to these gears, and they're physically moving them around the sun. And in Descartes' theory, this ether vortex theory is what it was called. It was a fluid called ether, and it was spinning around in a vortex. That, again, you have this fluid that's in contact with the planets, and that is dragging them around the sun. So both of these theories relied on this idea that things need to be sort of touching each other in order to be in motion. Or rather, for something to move, something has to kind of push it by being in contact with it. That's the idea behind it. And this really sounds pretty reasonable, right? But to us, nowadays, this sounds strange, perhaps. After all, we have been taught that it's gravity that pulls things around the sun, right? Or attracts things to the earth. Well, think about that for a moment. What do we believe now? We believe in gravity, right? This is our inheritance from Newton. But what does this theory of gravity tell us? It tells us that the sun is pulling on the earth across 93 million miles of empty space with no strings attached, there's no wires, there's no fluids, there's no gears or anything. There's this invisible force pulling the earth toward the sun across empty space with nothing attached. It's one of those things that, the more you think about it, the weirder it sounds, okay? And, if this isn't magic, like, I don't know what magic is, right? This is very, very strange. And this is precisely how Newton's opponents characterized his theory. They said, Newton, you are trying to reintroduce sort of magic into science. You're trying to bring the occult into science by proposing there's these invisible forces acting across empty space. So that was a pretty severe criticism of Newton's theory. And he actually tried to find ways around this. He wrote a lot about how maybe there could be some sort of invisible fluid being exchanged between the planets or something. But the followers of Newton really pushed this theory pretty hard. They said, no, things can act where they are not. There are these invisible forces pulling across empty space, right? And that's a theory we've kind of inherited. And this is really weird, okay? And I'm bringing this up because this is, I think, a perfect example where careful scientific observation, by looking at nature, there are deeper philosophical issues that are being raised, right? So what kind of entities can we postulate within a scientific context, right? So, is it only material causes? Is it only matter and the interaction between matter, like fluids pushing up against things and gears pushing on things, or even atoms pushing up against each other when they're in direct contact? Is that the kind of scientific theories that we should be aiming for? Or should we also be talking about these sort of immaterial causes, invisible forces that you can't see or feel, right? And that's really a philosophical kind of issue. What kinds of entities can we even talk about within a scientific context, right? And when these sort of issues were brought up to Newton, what he tried to do, these are deeply philosophical issues, and Newton really tried to address these issues head on. In fact, in some of his books, in his book called The Optics, and his book called The Principia, the long title is Mathematical Principles of Natural Philosophy, but nobody likes to say that, so they call it The Principia. He tries to address this sort of issue, and he's trying to address these philosophical problems that these scientific theories raise. And I guess my question is, are we willing to do the same kind of thing, right? Are we willing to address these sorts of philosophical issues, or are we going to ignore these sorts of issues? Okay. So now, I guess after after this lengthy introduction, and to sort of whet your appetite maybe about how science and philosophy can be intertwined, I suppose, I want to talk a bit about the particular work that I've been involved in over the past several years. My particular field of specialization, I think I mentioned that it's the physics of fluids. And when I was doing my graduate work back in Santa Barbara around 2000, one of the fluid systems that I studied was liquid helium. And liquid helium is a really fascinating fluid, and I want to give you a sense of the kind of things that liquid helium does. You've probably experienced helium before, like in helium balloons. That's the case where helium most often occurs as a gas, right? But when you cool down liquid helium to very low temperatures, around 4 degrees Kelvin, about 4 degrees above absolute zero, helium becomes a liquid. And if you continue to cool liquid helium down more, it becomes what's called a superfluid. And I'll explain what I mean by this in a moment. It ends up having what's called zero viscosity. Okay? So to kind of explain how this works, let me use another example. I have a picture of a glass of wine over here to explain the topic of viscosity. So let's suppose you have a glass of wine, and you begin kind of swirling it around in your hand like this, and then you stop the glass from moving. So what happens? Well, the wine keeps swirling for a little while, but after some time it comes to a stop, right? So why does it come to a stop? Well, it's because it's a viscous fluid. So what's happening there is the layer of wine that's adjacent to the glass kind of rubs by friction against the glass, and the glass slows down that layer of wine, right? And then the layer of wine next to that rubs against that layer of wine, it slows that down, and so on and so forth. And so this viscosity, this interaction, or this friction between the layers brings the wine to a stop, right? So that's this phenomenon of viscosity. Now, liquid helium, if you get it cold enough, is very different than that. So I have a picture here. This is not a picture that I took. This is kind of a stock photo of a little bowl full of liquid helium. Liquid helium is very interesting because if you were to take this bowl of liquid helium and you get it spinning around somehow, however you want to do that, and then you stop it from spinning, what happens is the liquid helium that's inside will keep spinning, and it will keep spinning, and it will keep spinning forever. Okay? And by forever, I mean for as long as anyone has cared to watch. So maybe there's some graduate student watching this still, right? So it has literally zero viscosity, which is just fascinating, right? It's a very strange substance. So why am I bringing this up? Well, in a sense, the case of liquid helium is sort of the opposite of gravity. What do I mean by that? Well, in the case of gravity, you have two objects, the Earth and the Sun, and there's a force of interaction between them across empty space. So 93 million miles of empty space. This thing over here is pulling on this thing over here, despite the fact that they're really far apart, right? With the case of superfluid or liquid helium like this, you have two things that are rubbing up against each other, the glass and the liquid helium, and yet there's no force of interaction between them at all, right? So it's this very strange situation where you have things touching that normally exert a frictional force between them, and yet there is not, right? So in a sense, it's sort of the opposite of the case of gravity, at least in that sense, right? Yeah?
How do you make liquid helium?
Right, so it takes very powerful refrigerators. Okay? So the helium was first liquefied by a guy named Kamerlingh Onnes in the Netherlands back in, I think, 1904 perhaps. So there was kind of a race to liquefy every gas. You know, scientists are competitive. They say, I liquefied oxygen. Oh yeah, I liquefied neon. You know, so they were liquefying all these gases. And basically what they do is you have to compress the gas, and then when you expand it, it cools, and if you do that over and over and over again, you can liquefy it. So you might be familiar with, like, if you have an aerosol can where you have to compress the gas inside, and when you spray it, the can gets cold. Have you ever noticed that? Yeah. So that's the basic idea. You get this kind of this expansion of this gas, and in expanding, it cools down, and you can kind of, it's tricky to do this. You have to do this over and over and over again to the gas, and then it eventually turns into a liquid. So is that fair? Yeah. So anyway, the person who first liquefied helium, that was the last gas to be liquefied. That was, I think, in 1904. And he's also the one who discovered superconductivity, I think in 1909 or 1911. And he thought it was an accident. But that's a whole other story. So that's interesting. So I have another thing on the right. So this this picture on the right, I just thought this was neat. I came across this while I was doing, preparing for this talk, and I'm just putting this in because I thought it was pretty fascinating. This is the opposite case of liquid helium. On the right, this is apparently an experiment at the University of Queensland. It's a pitch drop experiment. And apparently this pitch, so there's kind of this jar around it. I don't know if you can see it. And there's this glass funnel. And this experiment apparently was set up in 1927. Okay? And this pitch has been dropping through this, one drop about every 10 years since 1927. Right? So this is a case of an extremely viscous fluid, right? So I just thought that was kind of neat. It's sort of the opposite of superfluid helium. So I've used the term superfluid helium a couple of times, and that's a term that people who research helium and these very peculiar properties of it call it. They call it superfluid helium because it has these kind of amazing properties. It acts like an amazing fluid that flows without any viscosity whatsoever. So it's a neat system to study. Any other questions at this point?
I have one.
Sure, please.
How does the container not slow down the liquid helium?
Right, so
Rubbing it.
that's a good question. And so liquid helium is what's called a quantum fluid. I'm not trying to slow you by throwing out the word quantum, right? But the idea is you might have, if you've taken, have you taken maybe some courses where you learn about energy levels or something? Okay, so with the theory, I'm going to give kind of a simple example here. So with atoms, electrons orbiting the atoms, you might remember this from your science classes back in high school or college or something. These electrons orbit the atom, but they can only exist in sort of discrete energy levels. They kind of hop between these. So they can't exist in sort of this continuous state between those two levels. They have to be here or here. Well, a fluid like liquid helium, when you cool it down enough, it behaves like what's called a quantum liquid. And when it's flowing, in order to slow down, it has to jump to a different energy state that sort of, there's a kind of a gap through which it has to go. And it can't do that. So it stays in this state where it's spinning around. And so it does it sort of, in order to interact with the walls of the chamber, they have to exchange energy with them, but there's sort of a quantization of the energy. So that's sort of an explanation of why that works. Is that helpful? Okay. So, I mean, this is my work with liquid helium is stuff that I did kind of back when I was a graduate student. It's pretty expensive to do. You have to have really powerful refrigerators and so on. So when I came to Wisconsin Lutheran College, it's a small college, I moved to room temperature fluid physics, which is a little bit less expensive. These are not images I took, by the way, but I'm going to introduce the kind of work that I'm doing at Wisconsin Lutheran College. So, as I mentioned a moment ago, fluids, generally speaking, have viscosity, right? So if you take a ball and you drop it in air, it will fall. If you drop the same ball in water, it will fall, but a bit more slowly. And if you take the same ball and you drop it in honey, I don't know if you've ever done this, but if you did, right, it would fall more slowly yet. And that's because honey is more viscous than water, and water is more viscous than air. So kind of like how fast it falls depends on the tackiness or the viscosity of the fluid. And this is something that engineers are very interested in, right? So when they're designing cars or airplanes, they want to make sure that the car or the airplane kind of deflects the air around it so that there's a minimum interaction between these two things. So if you've seen on car commercials, they'll show the car in a wind tunnel, right? And there's the air going around it, and they want it to be aerodynamic to reduce drag and increase fuel efficiency, right? So one can do this in the laboratory, and these are some images by a guy named Van Dyke. He wrote this sort of famous book about drag and viscosity and flow around obstacles. And in the upper left-hand corner, what this depicts is he was taking fluid, I think it was water actually, but I don't recall, and he was making it flow from the left to the right, and he immersed this cylinder in it. So you kind of have to imagine there's a cylinder, a bar kind of immersed in the fluid, and then he sprinkled these, I think there were mica flakes in it, and then illuminated it, and that allows you to kind of see the flow going around this cylinder, right? And so you can see these sort of streamlines going around the cylinder, and generally speaking, when the flow is very slow, or comparatively slow, you get these nice kind of smooth streamlines around this object, right? So you see this nice smooth streamlines around the object. That, by the way, is called laminar flow. That's a term that's used for it. And as you increase the speed of the flow, what happens is you still get this nice laminar flow. So you go from A down to B, you get this nice smooth laminar flow around it, but you get these sort of little eddies, like a wake behind it, and there's kind of these spiraling eddies that are behind it. And as you increase the speed of the flow, what happens is the size of those eddies get larger and larger, okay? And then what happens, and this is interesting, what happens is that if you increase the flow to just the right speed, the wake that's behind the cylinder, this sort of wake that's appearing right here, becomes unstable and it kind of starts waving back and forth like this. And then it becomes unstable, and you get a situation like what's shown in the upper right diagram. Okay, so here, the cylinder is on the far left, and we kind of zoomed out a little bit. But what happens is that wake becomes unstable, and it displays this kind of beautiful pattern of these vortices, these spinning regions of fluid that are kind of shed off of the cylinder. And it's very interesting because it's sort of a periodic shedding of these vortices. And you get these really beautiful images of these vortices showing up behind this. Okay, and you know, this might, I think this one was marked, I think we maybe put some milk or something in the fluid to be able to visualize this. And you actually might have seen this kind of thing before and not realized it. If you've ever been like swimming in a pool or something, or maybe in a glass of beer or something, you might see this. So you sometimes see bubbles, and bubbles rising through a fluid, sometimes you'll see them kind of wiggling a little bit like this. I don't know if you've ever noticed that, like bubbles wiggle. Well, that happens because if the flow around the bubble is just the right speed, like this, you get these, what's called Kármán vortices behind it, and so what happens is this vortex kind of gets shed that way, and the bubble jumps that way, and then it gets shed that way, and it jumps that way, and it gets shed that way, and it jumps that way. So you're basically having this vortex shedding, and it's going up like this through the fluid. Okay? You just can't see it because the fluid isn't marked with some kind of markers to be able to see it, but that's actually what's happening. Okay? So these sort of things happen in nature, but generally speaking, you have to get the flow speed just right to observe these kinds of patterns. In the lower right diagram, as you increase the speed of the flow faster, and I'm showing something that's going very fast. This is a picture of a bullet flying through air, right? And now you get what's called this turbulent or chaotic flow behind the bullet. So this right in here, this is no longer this smooth laminar flow. You get this kind of churning, this chaotic, turbulent fluid behind the bullet. And you get these shock waves as well. This image is actually from using a technique called shadow graph photography that allows you to visualize these sorts of things. Okay. So between these two extremes of this kind of turbulent, chaotic flow and this nice, smooth, laminar flow, you get this kind of beautiful, periodic pattern showing up in nature. It's kind of really, really neat to see. So in my research lab, so this is kind of by way of introduction to this topic, in my research lab, what I'm trying to do is study this sort of thing, this transition between the smooth laminar flow and this turbulent flow, and look at the kinds of patterns that appear in these fluid systems. And the way that I'm doing that is by studying soap films. Okay, so we're familiar with soap films, right? Soap bubbles, delicate little bubbles that form. It's kind of, I thought it'd be fun to show this. So I built these little, I was doing wiring in my house actually. And I had extra leftover copper wire, and I thought you could do this. I thought this would be fun, so I soldered these wires together, and I dipped them in soap solution. You can get these kind of neat square bubbles and triangular bubbles and things like that. That was kind of cool. But you might have noticed that when you look at soap bubbles, oftentimes you can see these sort of swirling colors on the surface of them, right? Kind of reds and blues and yellows and greens. And those colors tell you something about the thickness of the soap film. Okay, they kind of contain that information in it. So depending on what color it is, it tells you how thick the soap film is at that particular location. And by looking at these colors move around, you get a sense of how this bubble, the fluid in the bubble, is flowing around, right? So what we can do is try to get a little bit more scientific about this. So what we did in my lab is we set up a light source. Okay, this is a little cartoon in the upper right corner where I show a light source. This is a sodium lamp, so it produces this red light. And this ring right here, you might imagine a ring maybe about that big, made of copper, and I stretch a soap film between it, and then I've got a camera set off on the other side. And then you can capture these images. This is using a Canon camera with a macro lens. You get these kind of beautiful swirling soap film patterns. So this isn't any false color or anything. This is the actual color it is when you bounce this red light off of it, and you get these kind of neat swirling patterns. Right? Beautiful patterns like this. And in the upper left corner, I show the scale. Those, I guess it doesn't tell you the scale because it's units on it, but those are millimeter markings there. So I'm actually zooming in pretty close so you can see what's happening on this soap film.
Sorry, do you scan it live or not just focus?
Pardon?
Just scan light or just focus in the point?
Do I have to focus?
Scan, yeah.
Oh no, this is just I'm just focusing on the soap film. So what makes it hard is, so I hadn't done photography before this, so I'm trying to learn a lot about photography right now, which is really hard because in order to let a lot of light in, you need to have the shutter open a lot, but then you have a very narrow depth of field, right? So I need to have a smaller aperture size, but then I get a narrow depth of field. And so it's hard to get the whole thing in focus, especially because I'm off to the side and I'm taking it at an angle, right? So there's some tricks to doing this right. This took my students quite a while to get these ideas, right? So there's a lot of kind of work that goes into doing this kind of imagery. Did I answer your question?
Yeah.
So yeah, this is.
I think his point was that in your cartoon at the top, you're showing a small beam.
Oh, got it.
Right? And it's not illuminating the whole area.
Right.
I was wondering, are you scanning the beam, or is your beam really large?
It's larger than that. So I actually had to expand the beam a little bit and use a lens and make a broader particle illumination. So yeah, good. Thank you. Okay. But what I'm interested in here is not just static soap films, right? But I want to look at these flowing soap films because I want to try to look at how fluids flow around objects. So what some of my research assistants and I did is built this piece of equipment to measure falling soap films. And this is not something we came up with, actually. There have been researchers who've done this kind of thing over the past 15 years or so, 20 years perhaps. And I show a diagram of it on the left-hand side. So up here, what we have is a kind of a reservoir, and in that reservoir we have a soap solution. It's just water with Dawn liquid, there's nothing fancy, right? And then below it we have a little valve, and these wires here are actually just some fishing wire, some fishing line, okay? And I have a weight hanging at the bottom, and when you open the valve, the soap kind of dribbles down these fishing lines. It sounds really low-tech, right? So we've got this soap dribbling on the fishing lines, and then what we do is we take these other strings and we pull it apart, and then you get this soap film, like a big bubble between this. And this apparatus is, about probably 7 feet tall or so, 7 or 8 feet tall, and we pull them apart probably like, 10 centimeters or so. And then we get this soap film that's falling. It gets collected in this tray down there, and we take a pump and pump it back up to the top, and we just keep it continually circulating. And you get this soap film that falls, and you can have it falling like that for, 45 minutes or so, if you're careful. Okay, to keep it nice and clean. And on these diagrams here, I show some of the images of the apparatus that we built. I have a couple of research assistants, Amelia Louth and Elise Slowey, built this apparatus. And so here you can see this reservoir with the soap solution up at the top, and then some tubes, and then the fishing lines are right here. I put some white lines over them so you can see them a little bit better in this diagram. And at the bottom, they come in like this, and there's the weight, and then here's the pump. We pump it back up. And then here's the interesting thing, is that we have a little motor that we control the computer that inserts a little obstacle into the soap film. And if you do this really carefully, you can insert an obstacle into the soap film without popping it. Okay? Now you can actually do this with soap films. If you take like a toothpick and you moisten it, you can stick it through a bubble without popping the bubble. Try that, right? So if you do this just right, you can stick it through without popping it. And then what you can do is you can look at, as the soap film is falling past this object, the kind of wake that forms behind it, or kind of the pattern. Is this the beeping that you told me about? So what do I have to do? Oh, that's what I gave you. Gave me the card for. This is the professor's been talking for too long. So we can look at this, how the soap kind of flows around these obstacles, right? And so here is one of the first images that we got. We were not being very scientific here. We just took a piece of Tygon tubing or rubber tubing and kind of stuck it through and wanted to see what it looks like. This is an image. This is a movie, actually. So you can see, so this is what the soap bubble looks like as it's falling down. You can see this wake kind of forming behind it. Over here is the fishing line. You can't see it very well. And they turned off the valve, so the soap looks kind of psychedelic, right? You can see the soap kind of swirling around like that. And then it pops here in a moment. Okay, and now we try to be more scientific about this. So now we got the... And now you can see kind of this wake forming behind this obstacle as the soap is going past it. Let's go for a second. we're using a Canon camcorder, a 70mm macro lens, and we have, in this case, it looks blue because we're using a mercury lamp to illuminate it. In this case, we're trying out different kinds of lamps and whatnot. Okay. So that's a movie, and here's a couple of still images. So now we're trying to be a little bit more scientific about this. Instead of just taking a piece of rubber tubing, we use this motor to stick a plexiglass rod into it very carefully. And this plexiglass rod, you can kind of see it right here. You're kind of looking head on. It's coming out like this. Through the soap film appears green right here. That just has to do with the thickness of the film. And you can see this really nice wake behind this obstacle. And then as we speed up, you can increase the speed of the flow. And then you can see that this wake starts becoming unstable. It starts kind of wiggling back and forth at some particular speed of flow. You can see that happening here, though, this kind of wiggling. And then if you go to just the right speed, then you get these kind of Kármán vortices forming behind it, right? So you get this beautiful pattern forming. And you have to really control the speed very carefully to get this to happen. And this is actually the same light source. There's no false color or anything here. This is actually what it looks like. What is misleading about this is that you can't actually see this with your eyes. You can't see these vortices with your eyes because it's happening so fast. It's just like a blur behind it. So you have to use a very fast shutter speed in order to capture this. And the camera we're using a Canon Rebel EOS T6i. The fastest shutter speed we had is 1/4000th of a second. And it still looks a little bit blurry. It didn't look as crisp as we wanted it to. So what we did is there's a buddy of mine who's in the engineering department at Marquette University down the road from us, and he studies ballistics, so he's got this really nice high-speed camera. It captures like 100,000 frames per second. It's one of these really expensive cameras, right? So he let me borrow it for a couple of weeks. And the drawback with this camera is that you sacrifice, it's not a color camera, right? So it's going to be black and white, but you can get really high-speed images. And so you can see here's some images we took with that. We've got the cylinder sticking up right there, and you've got this vortex street behind it, right? This kind of beautiful pattern appearing behind it. And likewise here, this is actually a movie. I'll click it to start it in a moment, but I should warn you beforehand. So the light we're using, like all lights, has kind of a flicker to it. But this flicker happens very quickly. Like fluorescent bulbs, they flicker. It just happens so fast your eye doesn't see it usually, right? But when you're taking images with a high-speed camera, you can see that flicker, okay? So if you get headaches from seeing things get like bright and dim, close your eyes, you don't have to watch this, right? But you're gonna see it kind of get brighter and dimmer, and that's actually the flicker of the light, okay? That's happening, I think it's 60 hertz of that flicker, like that. So, but you'll see what this looks like, and this is at 3,000 frames per second, and we're using 1/8000th of a second shutter speed. This. And you can see that flicker. It's kind of maddening, but you should get that light source. Is that some film noir or something? And then we have another one right here. So this is the other one. And the frequency that these vortices come off at depends on the flow speed. So the faster the speed, the kind of more rapid they come off. So kind of by tuning the frequency, you get different frequencies of shedding into these vortices. Okay, and let me stop that. Okay, and here's one more movie. So what I did here is I turned it sideways and zoomed up on it a little bit. So it's still, this is soap film falling past it, but I turned it sideways so it looks like it's going from right to left. And again, here is the end of the cylinder sticking through it, and you can see this pattern forming behind it. This. I think it's sort of neat how you can see sort of these other vortices kind of curling up into it and being kind of encapsulated by that as it's moving downstream. So it's kind of turbulent inside of that core, but around it, it's got this nice periodic flow. So, we worked pretty hard to getting these images in the lab, but these things don't just happen under controlled laboratory environments. So I'm going to show you some images here now. These are not my images, these are NASA images. And so on the left, this is an image from the recent Juno probe taking pictures of Jupiter's atmosphere, right? And it looks very kind of turbulent and chaotic, but if you look closely, you can see sort of this little bit of structure and order in there, right? There's sort of some patterns you observe there. And I thought this was a really neat photo. This was taken, I think, in like 1999. It was a satellite photo, and it was a kind of fortuitous or lucky coincidence that they were able to capture this. These are some islands off the coast of North Africa. And the atmosphere is flowing this way. And these islands are kind of, there's mountains, and they're sticking up through the clouds, okay? And as the clouds are going past, the speed must be just right that you're forming this vortex pattern behind it like that, right? You see that? So you got these vortices forming behind it. So it must have just been just right conditions. You get this beautiful pattern, So we're working really hard to get everything right, and then you see this kind of thing happening in nature, right? So it seems that sort of these beautiful patterns that you can create in these fluid systems, you can also notice them in various situations in nature. And I think this is a broader point that I think is very interesting about this kind of research, is that we see these patterns in nature all around us, right? So we see patterns in fluids, we see them in trees, in animals. There's sort of this orderliness in nature that's very, provocative. It's interesting. Where does this order come from, right? And here's where I want to raise a broader question, right? So I think that when you look at nature, there are some kinds of complex patterns or objects that seem to and obviously require a person to make them, right? So when you have a musical symphony, you hear a musical symphony and you know immediately, somebody wrote that. It has a signature of an intelligent person that generated that music. And that's the case not just with symphonies, but with paintings and with, computers and various engineering objects, right? So you know immediately on looking at this that a person created, there's an intelligent being that did it. Other times you have these complex patterns or objects in nature that seem to not require any kind of artist or designer in order to exist, right? So take a snowflake, for instance, right? It's not like someone built the snowflake, right? But snowflakes exhibit this kind of beautiful symmetry in these patterns, right? And that's the case with snowflakes, it's the case with plants and animals. It's not like you had somebody build a plant, right? You've got these plants that are exhibiting this order in nature, right? And I think here's the broader philosophical question that I'd like to raise is that what if these first glance conclusions, either of them is incorrect, okay? And I think this is something that people have struggled with over the years. In other words, think about the first one. You've got these complex patterns where you're sure a person, there had to be an intelligent agent that did it. What if, really, all of this idea we have about agency and intelligent people doing actions can be reduced to simple physical laws, right? The idea that everything can just be reduced to atoms and their interactions. That's something that people have really pushed, right? So that's kind of a reductive view of nature. It seems like, we're people that have wills and desires and goals and so on, but maybe it's all just mechanical interactions, and it can all be reduced to sort of chemical interactions and atoms bouncing off of each other, right? So what if our first glance ideas are not correct, okay? And on the other hand, what if the things where we think there's sort of this spontaneous order appearing in nature by the laws of nature, what if to really fully understand these, to fully understand them, we need to invoke the action of sort of an intelligent, purposeful, a purpose behind it, an agency, a soul, a God, right? And these are questions that people have wrestled with for centuries, right? So, and these are probably things that you've thought about before too, right? So, I can't really, I don't think I'm going to be able to answer this question, these sorts of questions to your satisfaction. You know, these are deep questions about how nature works and what's the source of order in nature. And this is, I think, one of those cases where doing scientific research draws you to these broader philosophical questions that have theological implications, right? And this is one of the main points that I'm trying to make here. And maybe instead of trying to give you evidence one way or the other right now, what I'd like to do is kind of present you with a few opinions or judgments that famous scientists and thinkers have come up with over time of how to think about these issues, right? So that's what I'm going to do over the next couple of slides here. Is there any questions at this point? Yeah, please.
I remember a long, long time ago watching a program on the chaos theory and just how patterns just show in chaos, when you just take randomized subjects and how you still see a pattern. And yet, not any pattern is a particular pattern that's precisely like the other one.
Right.
And it's just, they're beautiful patterns when they just
Yeah, I think that's something people are good, like when you see something, you have a recognition, well, that's beautiful, right? There's something about it that's really neat. And then when you think more about that, like why is it like that, right? So what is it about nature, or what would it require to fully understand? Right? What kind of things do we have to appeal to? Is this simply reducible to just matter? Or is there some kind of, do you have to invoke some kind of agency or like some designer to try to understand why this would be like this at the deepest level? And those are hard questions, right? Those are really hard questions to address. So I'm going to present you with maybe 5 or 6 opinions by people and then talk a little bit more about this. So here's a quote by a 4th century Greek thinker named Democritus. He's one of the people who's credited with coming up with the atomic theory, the idea that things can be reduced to atoms, right? So atoms make things up. And what he's presenting us with here is a very reductionist perspective, that everything we see around us, kind of all the order we see around us, all the complexity, all of our thoughts and so on, can be reduced to just the motion of atoms. That's sort of this very materialistic perspective, right? So he says, by convention sweet, by convention bitter, by convention hot, by convention cold, by convention color, but in reality atoms and void. Right? It's a very stark perspective of it, right? Everything can just be understood in terms of atoms and void. That was the kind of the argument that Democritus had. Here I have another much more contemporary scientist, well, much older, much more recent scientist. So this is James Clerk Maxwell. He wrote this in 1873, and it was actually a dictionary entry. He was asked to write a dictionary entry for molecules. So back when, I'm sorry, encyclopedia entry, back when people used encyclopedias. You look up molecule and somebody wrote that. So Maxwell wrote that molecules entry in one of the encyclopedias. He was a very famous scientist. He developed the theory of electricity and magnetism. He was an English scientist, and he also developed a lot of the theory of heat that we still learn as students of physics and graduate students. And he also was an atomist, so he kind of argued forcefully for atoms, but one of his arguments was that atomism actually directs the mind to God. He said, if you think about atoms, it makes you think about why they're like that, which naturally draws your mind to a creator. Okay? And specifically, he argued kind of like this. He said, when you see a pyramid, and the pyramid is made of a bunch of bricks, and all those bricks are rectangles, right, or prisms that have the same size and same shape, kind of the identity of the bricks leads you to believe that somebody designed those bricks. The very fact that they're all the same makes you think somebody obviously did this. And this is the way he argued about atoms. He said the exact equality of each molecule to all others of the same kind gives it, as Sir John Herschel, who was an astronomer by the way, has well said, the essential character of a manufactured article, and concludes the idea of its being eternal and self-existent. So what he's arguing here, again, is that the fact that every molecule of the same type, like every methane molecule or every nitrogen molecule or so on, because they're all the same, this is a clue that they look like things that were designed. Now, you may agree or disagree with this, right? But in his judgment, this was indicative of a designer who made the molecules. Okay, this is how he argued. here's a quote going back to ancient times. So this is Aristotle. This is from his book called Physics. This is book 2. I actually have my students in one of my classes, my astronomy class, read some selections from Aristotle. And what he's doing in this quote, he's actually not presenting his own theory. He's presenting the theory of another scientist called Empedocles. And Aristotle actually disagrees with this perspective, but he's kind of summarizing what Empedocles' view is. And Empedocles argues something like this. He argues that we've got all these different animals in nature, and it seems like they have a purpose to them, but really I think that they were just sort of spontaneous. All kinds of animals were spontaneously generated, and then nature sort of selected out the ones that were most fit, and those survived, and the ones that were not fit, they died away. Okay, that probably sounds familiar to you. Okay, this is Empedocles' idea, and so this is Aristotle relating it. He says, why then should it not be the same with the parts in nature? For example, that our teeth should come up of necessity, the front teeth sharp, fitted for tearing, the molars broad and useful for grinding down the food, since they did not arise for this purpose, but it was merely a coincident result. And so with all the other parts in which we suppose that there is a purpose. Wherever then all the parts came about just how they would have been if they had come about for a purpose, such things survived, being organized spontaneously in a fitting way, whereas those which grew otherwise perished and continued to perish, as Empedocles said. So Aristotle was relating to us this view that this scientist had, and this sounds a lot like natural selection, right? Aristotle disagreed with this entirely. He said this is not, this kind of chance explanation, he said, isn't an adequate explanation of nature. In fact, Aristotle, and he wasn't a Christian, of course, right? So he wasn't coming at this from a Christian perspective, but he argued that chance doesn't really provide, if you're looking at understanding something, chance can't really provide understanding. It's sort of a way of waving away things and saying, that's just, that chance explains everything. Well, what does that really tell you? So Aristotle was very critical of this perspective. Okay, here I have another one. So Nicholas Copernicus. I saw you have a Copernicus street up here. So this is a quote on the revolutions of the heavenly spheres. This is where he is explaining his theory of planetary motion. And Copernicus is talking here about, by looking at nature and sort of the patterns and the order in nature, it implies the existence of, he calls it an artificer, a divine artist, a god. Okay, Copernicus was a Catholic, and he basically argued that looking at nature presents you or immediately confronts you with the idea of a designer. He says, for who, after applying himself to things which he sees established in the best order, would not wonder at the artificer of all things? And he kind of develops this thought. And this is what's kind of fun about reading some of these older texts, because these scientists, they're presenting these scientific ideas, but within the scientific context, they're presenting these kind of theological arguments and philosophical arguments, and they're intertwining these together. And that's really not something you see, when I pick up physical review letters or something, that doesn't happen, right? So, and you can argue whether or not that should happen in a scientific text, but it was very common, probably up until the 1900s, for a scientist, when they're presenting their views, not only their scientific views, but kind of giving a philosophical or theological backdrop for explaining what they're doing. And so when we read these things in class, it provides a nice avenue to talk to the students about these sorts of things. Do you agree with this? Do you disagree with this? And so on. Here's a quote by Stephen Hawking, okay, famous astrophysicist, passed away a few years ago, from his brief history of time. And here, in a sense, Hawking is agreeing with Copernicus' view. He's saying it seems like there is this design in nature, but what's not included in this quote is he actually totally disagrees with it. He says it's an apparent design, but that's illusory. In reality, everything can be reduced to purposelessness, right? So there's not a designer behind it. But this quote kind of captures, it seems like he's agreeing with Copernicus, but then he turns around and says, but this is all an illusion. It's not really the case. He says, the laws of science as we know them at present contain many fundamental numbers, like the size of the electric charge of the electron, and the ratio of the masses of the proton and the electron. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life, right? So it seems like they've been tuned just right. And this is a problem for physicists, right? Why is it that it seems like all these kind of fundamental numbers and quantities that show up in nature seem to be just tuned just right to allow for the existence of life? Copernicus argued, well, duh, it's because there's a God, right? And Stephen Hawking says, well, there must be some chance explanation, or there must be some other explanation. Here's the last quote I want to give you, and this is, I'll give this a shot because I'm in Ottawa. This is by Julien Offray de la Mettrie. Okay, so he was a, I guess you might call him a brute materialist. So he basically believed that all living things ultimately are machines, right? So they seem to have emotions and whatnot, but it can be fundamentally reduced to mechanical interactions, right? So he says, let us then conclude boldly that man is a machine, and that in the whole universe there is but a single substance infinitely modified. So this is a very reductionist view. Matter is all that there is, and inanimate matter is really all that there is. And we have this sort of illusion of sentience and so on, but it's really can be reduced to material causes. I think when examining these sorts of quotations, it's important to recognize that none of these thinkers are presenting you with evidence. What they're presenting you with is their judgments that they have made based on the evidence that they've seen, right? So they have reasons for believing what they believe. They have examined things, they've read, they've studied, they've done experiments, in some cases, not all cases, some cases they've done experiments, and they're presenting us with their judgments, their assessment of how to interpret the data. We all have the same data. The question is how do we make sense of it? How do we interpret it, right? So it's important to recognize, when Maxwell says, I'm looking at these atoms and they're all identical, and that seems to point to the existence of a God. That's his judgment on it. Likewise, when Stephen Hawking says, this looks like things are organized in a particular way by design, or not, there's really no designer behind it, he's presenting his judgment about that, right? His view, his best assessment of the data, right? And I think this raises a question for all of us, is how do we make our judgments, right? We have to make judgments about things. We withhold judgments in some cases, but we have a tendency to try to assess the scenario and make judgments based on the evidence that we have. And the question is, how do we make those judgments? And in particular, how much do we rely on authorities, right? How much do we rely on people who've done the experiments, and how much should we kind of go out and do this stuff ourselves and try to analyze it ourselves? Because that's very time consuming, right? If we had to do the experiments ourselves every time, that takes a lot of time, right? So how much can we rely on the judgments of authorities, and how much should we rely on sort of experimentation and observation? And this is a hard question to answer. So I guess in talking about this, I want to talk about one more thinker. And this is a thinker named Blaise Pascal. So he was a contemporary of Galileo and also I think Descartes as well. And so let me go to the next slide here. So Blaise Pascal was a famous mathematician and a scientist and a philosopher as well. And he wrote a book called his Treatise on the Equilibrium of Fluids. My students read part of this in one of my classes. It's basically presenting his theories about atmospheric pressure. Okay? But what's interesting about this book is that he begins this book by situating his scientific work in a broader philosophical context and a theological context. His whole introduction is trying to explain the ideas of authority and reason. Okay? And in what cases one should rely on authority, and in what cases one should rely on reason, or we might say experimentation. Okay? And in particular, he argued in this way. He said, there are certain areas of study that we must rely upon authority or authorities. In particular, he said, for example, in history, and in law, and in geography, and in theology, one must, whether you like it or not, rely on authority or authority. So, for example, he said, if you want to know who the first king of France is, you can't go into your laboratory and kind of, using test tubes and whatnot, find out who the first king of France was. You must read books, right? You must rely on the authority, the witness of the people who were there and who saw this and who recorded it, right? It's the same thing with geography. He says if you want to know where the first meridian was laid, you can't like figure this out in the laboratory, in laboratory experiments. You have to go to the geographers and read their texts and say, we decided to put the first meridian right here. And likewise with language, if you want to understand how, how the ancient Greek grammar works, you can't do this in a laboratory, right? You've got to go to ancient Greek texts, try to analyze them, and understand how Greek grammar works. You must rely on authorities in those cases. In other cases, particularly, he says in other fields, one should give preference to reason or experimentation. And he says, for example, when you're doing mathematics or physics or chemistry, natural sciences. Okay? And he gives this kind of example. Actually, I don't remember if he gives this example. But so if you want to know what temperature it is outside, right, you could ask somebody, and use the weatherman as an authority, right? But in principle, you could take a thermometer outside and measure the temperature for yourself, right? Likewise, in mathematics, if you want to know whether, some mathematical proposition, like whether the sum of the internal angles of a triangle add up to 180 degrees, some mathematical postulate like that. Like, you could rely on an authority who tells you that. But you can also try to go, if you're adept at this, you can try to go through a mathematical proof of this. You can, you can try to measure the angles and see if they add up to 180 degrees. So you can experimentally check this, right? And his argument here was that there are certain disciplines where, whether you like it or not, you must rely on authority or authorities, and other ones where you should give preference to experiment and observation. Right? Does that make sense? What he's getting at here? In Pascal's time, the reason he was saying this is that he was presenting kind of a new theory of atmospheric pressure. And his opponents were telling him, saying, Pascal, you're all wrong, and you know why we know you're all wrong? Well, because Aristotle wrote a book, and his book said, nature abhors a vacuum, and so on, and so your theory must be wrong because it contradicts these ancient texts. And Aristotle was kind of trying to break away from, Pascal was trying to break away from that. He's saying, we want to respect the authorities in some cases, but we can actually do these experiments and check this stuff out, right? So he was kind of pushing back against the excessive reliance on authorities in areas where they shouldn't be given precedence. And that's what he was kind of forcefully arguing, right? Notice he wasn't saying we should never pay attention to authorities, but we should give precedence to authorities in certain cases and not in others, right? That's what he was arguing. I suspect, it's hard to speak for Pascal, right? But I suspect that if he was around today, he might have the opposite problem, right? I think in our society today, it seems like there's this excessive respect for empirical kind of experimentation in the sense that if you can't experiment on it in the lab and demonstrate it in a lab, then it's nonsense, or we shouldn't be talking about it, or we shouldn't really put stock in it, right? It's sort of this, if you can't measure it, then it didn't happen, that kind of adage, right? And I think this is a problem because it discounts areas where you really need to refer to authorities, right? So if you want to know when the University of Ottawa was founded in 1848, I guess I looked that up, right? So who was involved in that, you need to appeal to the authorities, the people who wrote the books, who were there, who saw it, saw the signatures and all that kind of stuff, right? Now, here's the trick though, is that not all witnesses are reliable, right? So there are cases, if you have many historical documents, the question is, which ones do you trust, right? There are some reliable documents, there are unreliable documents. These are things that historians have to battle with all the time, like which is the most reliable document? Were these people there? Did they see this? Were these people motivated by a desire to deceive someone, right? And so to the historian, the historical documents are kind of like the data in the same sense that to a scientist, a physical scientist, the laboratory experiments are the data, right? So in history, the question of is this document reliable is something you have to test, right? But in the end, the whole field of history is predicated on the notion that in some cases human testimony is reliable, right? If that wasn't the case, we couldn't do history. We shouldn't study it at all, right? So it's true we have to kind of discern which historical documents are reliable, which ones aren't, But once you're convinced something is reliable, you have to rely on it. Otherwise, you can't do history, right? And that's kind of the same in sciences. You have to ask these questions. Was this experiment reliable? Did the person do it right? Is the person a fraud? Did they do something incorrect? Are they trying to trick us? Those same questions arise in the natural sciences, right? But the laboratory experimentation is kind of the raw data in the sense that the manuscripts are the raw data. Does that make sense? You see sort of what I'm getting at there? And so I think this notion that's perhaps widespread now, that everything has to be sort of reduced to an empirical science, is destructive to fields like history. And this is where I'm going with this. You might see where I'm going with this already, is that it's also harmful to Christian doctrine, right? So if you're thinking about history, and much of Christian theology, not all of it, but much of Christian theology is based on the historicity of the teachings, right? So not all of the Bible, but some of the Bible is clearly presented as historical documents. So it says, Abraham was alive, and Moses led the children of Israel out of Egypt, and this most important document, saying the gospel saying that Christ died and rose from the dead, right? Those are presented as historical documents, right? And so it's not like you can go into the laboratory and determine if Moses led the children of Israel out of Egypt. You can't do that in the lab. And any assumption that you must is going to fail. In the same way, if you're trying to figure out whether Napoleon was alive, you can't do that in the laboratory. You have to rely on historical documents. And so the question is just, how do we treat historical documents, right? And I think this is sort of what I want to end on here, is that how seriously we take science in its domain, and how seriously we take history and historical documents in their domain, kind of maps onto how seriously we take theology and theological claims in their domain, and that's specifically an issue with Christian doctrine, because it's so tightly intertwined with claims on what happened in history, right, in real history. And I guess that's the point I'd like to end on, and I hope I've conveyed to you a sense of how scientific questions, in whatever field you're in, whether it's in science or in philosophy or in history or in political science, framing these careful questions within your discipline can lead to broader philosophical and theological issues. And really the only question then is, when these sorts of things naturally arise, and they do naturally arise, do we kind of back off from them and say we don't want to talk about that, or do we try to tackle it? Because someone's going to. And the question is, are we willing to do the same thing? So with that, I should stop, and I'd be happy to open the discussion to questions. Yes, please.
I have a question regarding your analogy regarding reason and the authority. In your analogy, you come to two different axes, something like perpendicular axis, something like the Cartesian, analysis. So we have a reason and we have authority. But they may be also in the same direction, maybe the two circles. One of them is the first circle, the second one is the bigger circle.
Can you develop that thought a little bit?
Something like that. For example, you can say, okay, the first circle is the reason circle, and after we have the bigger circle, which is the authority circle. And everything in the reason circle is inside of the authority circle. Or vice versa. You can say, okay, we have the reason circle, which is the biggest one, and we have the authority circle inside. So in this case, we have something like a paradigm, because when we talk about the paradigm, in the paradigm exactly talking about the paradigm, a big circle, which is mostly coming from authorities, and after we have the reason inside of those circles. So for example, if you go with the Christian authority, you will have the Christian reason. If you go with this, let's say, scientific authority, you will have the scientific reason. So maybe the paradigm are different, not those, So I think this reasoning and authority are not very separated or split from each other, something like rectangular. But I think they are more something like the two circles, one of them is the bigger one of them is the smaller one, and one of them is inside the other.
Do you think there's so you think one might be a subset of another one?
Yeah, exactly.
And which do you think is on the outside?
Yeah, I don't know. Those who are more materialistic leftists, they go with the authority. So the bigger one is the authority, the smaller one is the reasoning. I prefer reasoning to be the biggest one and the smaller one.
Yeah.
I prefer the
Is there an assumption that the authority, there's a power with this authority? Is this your definition of authority here? You said leftist in that.
Oh, okay. That I mean those who become I coming after the Kuhn, because Dr. Kuhn was the person who came up with the paradigm shift and the paradigm,
Thomas Kuhn.
Thomas Kuhn, yes, exactly. So for him, everything, any kind of the reasoning coming inside of some kind of the paradigm, and he tried to explain that, okay, when we have the old time paradigm, every reasoning coming through the paradigm, we can talk about it maybe based on the cognitive system, because if there are a lot of power, the power will generate some kind of the algorithm inside our mind. If that algorithm helps us to have a system of thinking, and many reasoning is coming up to those system of thinking, is coming by some power or something.
I understand what he's saying. Yeah, with the power in the algorithm.
Yeah.
Yeah.
Other question with regards to a topic I discussed in my philosophy class. So one of the things that we discussed in my philosophy science class was Klein's idea of a web of beliefs. So like, every person, they have a web of beliefs, and they may have different beliefs. So I think we would like to think that there's like an objective truth to the world, essentially, and we'd like to have our web of beliefs map onto the real world as closely as possible, right? But the thing that came up in that discussion was the fact that there are, for everyone, there's probably certain beliefs that we hold that do not rely on the evidence, or we discard evidence to keep our web of beliefs intact, kind of like the cognitive dissonance that happens, right? So my question, I guess, would be how do we know that, even if we see a source, whether it's evidence or from authority, if we read some a piece text or a piece of evidence, how can we be sure that that we can change our web of beliefs, and if we do change our web of beliefs, that we are certain that it maps closer to the real world than if we didn't change our web of beliefs.
Right. That's so short answer is I don't know. Okay, so that's a hard question. I think what you're asking is how can you be sure when you get new evidence that that's reliable enough and that it's not going to upset something else in a way that's actually going to make you adopt a belief system that's worse than what you're coming from.
Yeah.
Is that sort of what you're asking?
Essentially, yes.
Right. So you're kind of you're always doing it. You're sort of waiting. You're presented with new facts and you're weighting the evidence and you're kind of deciding, do I have to change my worldview based on this new piece of information that I have? And that's a hard thing to do, right? But we change our minds, right? We do change our opinions about things. So we're doing this all the time, right? And whenever we act in the world, we do this, right? But here we're talking about much more significant sort of decisions. We're talking about theological, worldviews. Those things carry a greater weight. So it seems you really want to get that one right? So, and I don't know, I'm not going to be able to give you some strategy for doing this, right? I think this is hard, right? And I know, we do this in the sciences all the time, and I think, Thomas Kuhn, he was a philosopher of science, talked about this sort of thing, so kind of related to that topic, is that scientists tend to be very conservative in the sense that if you've got a theory and it seems to work pretty well, you keep it because then at least you got something. You've got some way of wrapping your head around all the disparate facts and kind of making sense of it. But then things start kind of not lining up and you get these data points that are weird and you say, well, that guy's just not reliable, and that data point, but we'll worry about that one later. But eventually these data points add up in a way that your old paradigm, your old theory doesn't work real well. So then you've got to do the shift. And when you're kind of asking when you do that shift, how do you weight the data? And I don't think there's a strategy I can articulate to do that. It's something that everyone's got to do. Right? That was probably an unsatisfactory answer.
Yeah.
Rephrase the problem. Yeah, please.
I'm just wondering what you think are the compelling, authoritative accounts from history that compel you to think about God?
Well, I mean, so the Christian scriptures, really, so the Bible is presented as historical, much of it, not all, some of the poetry and so on, but even the poetry is talking about historical events in those places. But, the Gospels talk about the death and resurrection of Christ, and they're presented as, this wasn't, when the Apostle Paul was writing, he's saying, this didn't happen in a corner, this happened, everyone saw this happen, they're appealing to experiential evidence, things that people see, and the people who wrote these things down, many of them suffered martyrdom, for testifying about what they saw happen, right? Oftentimes, people will die for something that they're not, that they're deceived by, but very few, I don't know of anyone who would die for something that they know they made up, right?
Yeah.
So, I mean, I think the Gospels are a particularly important historical document, and they're really the foundational document of the Christian faith, right? Which shapes my worldview, right? I think there are some things in Scripture that are not presented as eyewitness accounts, right? So then you have to say, well, how do I treat those sorts of things, right? And then you say, well, how do these eyewitness accounts, like you're talking about Jesus, talking about the resurrection, now how, that suggested evidence that Jesus was God, right? And then how does he refer to these Old Testament documents, for example? Does he say these are historical, these are reliable? So that's kind of the way I think about this. So is that sort of what you're asking?
Thanks for that, yeah.
Okay. Right. Yes.
Are you a Christian, and do you believe in God, and why?
Yes. So why do I believe in God? That's a hard question to answer. I think in many cases, when people believe things, it's not like they make a choice to believe it, they just sort of do. It's sort of an intuitive thing that you recognize. It's more like you recognize you believe it, right? And I don't think that's just the case with theological things. I think it has to do with like whether you trust someone or not. You just recognize that you trust someone. It's not like you make a decision to trust someone in many cases. You just do. So it's hard for me to trace back why it is exactly that I believe in God, and specifically the Christian God, right? So, but now I look at it and say, I look at these historical documents and they make sense. It provides a coherent worldview, and that buoys my faith and my understanding. But I don't know if I would say that I read this and then I suddenly decided now I'm going to believe in God. It wasn't quite like that. I think it's more complicated than that. So. Please.
How many of your contemporary physicists or scientists would you say believe in God or the Christian God? And if they don't, what would the reasons that they give?
So I don't know what, I mean, there's those statistics, it's not like there's surveys. I guess there are surveys, but they're kind of self-filled out, right? So just kind of the people who are on both ends say, well, yeah, I believe in God. But it's not like there's some surveys that go around and say, I never got a survey saying, do I believe in God from the American Physical Society or something. So I don't know how many.
People
But I
that
mean,
you work with? Or?
right. So I mean, I know that, so when I was an undergraduate, I actually studied engineering. I was in what's called applied engineering physics. And my sense was that people studying engineering tended to be more likely to believe in God than some of the pure sciences. And maybe that just had to do with the fact that they actually had to build things that were. They had a sense of how things were not working, right? So that was my sense. In engineering, there tend to be people that were more theistic. In physics, I think, I mean, in my graduate program, I guess there were 16 of us in my class, and I know of at least 2 or 3 who were Christians or theists, and probably a couple of others were theists. There were only probably a couple that were sort of militantly atheist and would kind of argue that point. But I think it's all over the board, and I think I think we shouldn't assume that all scientists are atheists or I think probably in biology it may be I think in biology there's more pressure to abandon kind of a theistic viewpoint, more so than in physics. That's my experience. But that's not a reason not to study biology. Yes, please.
Yeah, just a comment to that. So I did study physics here at the University of Ottawa many years ago. And at that time, the dean, Dr. Benson, I had all of his physics books there. And then there was one book called the Holy Bible.
Oh, what?
The Holy Bible.
Oh,
And I asked him, why are you a Christian? And the answer basically they gave me at the time was, I'm not going to pretend that I'm so smart that I know everything. That was the end of the discussion.
Are you satisfied with that answer?
I was happy to know that he was willing to recognize that not everyone had all of the answers, and that not all answers perhaps could be answered by certification. Because of this, I developed a greater respect for him.
I know my advisor as an undergraduate, he was a Christian. But my advisor as a grad student was not. So, I mean, it's unfair.
I'm an engineer, and I've run into the authority and the scientific collision a lot. And for me, being a Christian and believing in God arises from the authoritative and the scientific collision of evidence. It's just there. Coming from nothing is too hypothetical. It's unconscionable. So maybe engineers, yeah, we like to build things that work. We have built things that fail. The iron ring in Ontario, in Canada, comes from a failed bridge. You learn you can't push on a rope. And that evidence, scientific evidence, where you can't push on a rope, it just all comes together into one conclusion. That's what always strikes me. It's this one conclusion. Sorry.
Yes, please.
So, like, I would build on your point where you said that in some fields we don't have to rely on authority, in other fields we rely on reason. For instance, in science we rely on reason, in geography and history we rely on authority.
Yeah. That was Pascal, by the way. I tend to agree with Pascal.
So, like, even in sciences we do have authoritative figures, and sometimes authoritative figures will present contrasting opinions, but there is still an underlying truism that we can find through reason, right? So, for instance, if I take the vaccine issue, there's Wakefield and his infamous study versus the mountain of evidence to his contrary. So, although we study these authorities in class, we can understand through more basic reason, through using chemistry and physics, to understand the biological reason of understanding each of these authoritative arguments. So we can weigh authorities and decide which authorities are more credible. So bringing that to a more theological and how that interfaces with other aspects, then how would you balance different authorities, because there are different religions, different Abrahamic faiths which may believe in the same God or different gods, but if you go into Hinduism or Buddhism, some believe polytheistic and some don't believe in God whatsoever. So how would you be able to use an underlying reason or truism to find which authority figure or which religion? Because there are many religions around the world, and a lot of us are talking about Christianity, but there's a lot of other religions, obviously. So how would you find the truism and weigh these authority figures when considering this?
Okay, right. So, great question. And Maybe I should just start out by saying that I do think there are elements of truth in all religions. I shouldn't say all, because I haven't studied all religions, right? But there are elements of truth, and that makes sense to me, right? So I mean, from a Christian perspective, we all have some kind of natural knowledge of God. And no matter who you are, you have a conscience, and you have some kind of natural sense of the soul, perhaps, and what's right and wrong, and that kind of thing. So I think there are elements. So if you read scriptures of other traditions, I would agree that there are things about them that I would agree with, right? I find the Christian documents and how they're specifically tied to historical events and how they're presented as historical evidence particularly compelling, right? And I think that's something that's weighted very strongly in Christianity, that's perhaps not weighted as strongly in some other religions, in the sense that I think some other religions perhaps focus more on sort of your philosophy of how you should live your life and so on, right? But Christianity isn't really primarily about how you should live your life. It's about whether Christ died and rose from the dead and what that means, right? So it's tied so intimately to this historical event, and then if that happened, like, that's kind of a game changer. That's sort of that seals it, right? If that actually happened, then that's really, really significant. And I guess I just find that very compelling, right? But I'll admit I'm not versed in I haven't studied enough other religions to be able to talk as intelligently as I'd like to about them. So, yes, please. I guess in the part.
How can religion withstand the test of time against science? If science continues to make discoveries that might lead us to believe that, that, for example, everything in the universe can be explained like in the absence of a creator. Meanwhile, religion isn't changing, it's basically stuck in time. Right. So I wonder how it can withstand the test of time.
Well, it can't, right? So I mean, it can't if one can demonstrate that the creator is unnecessary and any discussions about the creator don't make any sense, then Christianity would fail, right? As would all religions. But I don't think that is going to happen, right? So I mean, I think that the Apostle Paul was very clear about this. He said, if Christ didn't rise from the dead, then our faith is in vain, and we're to be pitied above all people. So it's really tied to this evidential approach to Christianity that, and if what you're saying is like, and I know you said if science disproves or proves that you don't need a God or something, but I think more broadly the point is that if you can demonstrate that Christianity, these events aren't true, or that it's incorrect, well, I think you're right then. I think Christianity shouldn't be followed. Right? Yes.
In your lecture, you've shown us nature patterns.
Right.
Like you've shown us patterns. I was wondering, in Ecclesiastes 3, it's saying, to everything there is a season, a time to be born, a time to die, a time for war, a time for peace, a time to gather, a time to scatter. And also I was reading a book called Passages by Gail Sheehy, and this book is kind of a 60s, 70s classic. And it's just a book about your 20s, your 30s. Like there's a chapter on people turning 20 and what that's about, turning 30, turning 40, turning 50. And also I saw the Truman Show movie. I'm hoping you all saw it. Because in the Truman Show, this movie stars Jim Carrey. It's about him, he's being filmed 24/7. And like, he doesn't know it, right? He's the star of a reality show. And so at the end he realizes, oh my gosh, like when his boat hits that wall, and then he realizes he's in a set, or he's the star of like a movie, right? He kind of comes to the realization, like actually Christoph, this man, he had a script that he wanted Truman to follow. Like he had this whole script, and he had the people watching it in masses. It was such a popular show. He reunites with his father. So I was wondering if our lives are scripted by God.
or if our lives have patterns. We all reach adolescence, we all reach puberty. Are our lives scripted? Are our lives have patterns? Like, and is this God's just will for us? I don't know. Do you agree?
Yeah.
Like you're showing us patterns in nature, right?
Can I dodge that question?
Okay, sure. It could be a crazy question.
As a scientist, sorry, you finished?
I was trying to dodge that question. So I think we have free will. I think we can decide what we want to do. I think that I mean, I know some people will argue that that's an illusion. I mean, but that's an assertion that I don't believe. So.
I have a question.
You want to,
I just have a curiosity question. As a scientist who's a Christian, when you're presenting scientific studies, do you ever run into a theological barrier with other scientists that are not Christian? And does that cause any animosity or any questions to your
It doesn't.
Just curious.
I mean, so almost never. If anything will happen like after the conference over a beer or something, and then you get into that kind of stuff, right?
Okay.
But like, I don't think those things don't typically come up at conferences, like these kind of, because, and I think, physicists and many modern scientists tend to not bring up those sort of controversial philosophical and theological topics at conferences. It's more like, here's the data, how do we interpret this data, and there's sort of those topics aren't discussed at many of the conferences that I go to. So, I guess the most, I remember when I went to a conference one time, and it was a keynote speaker, and I was pretty young at the time, and the keynote speaker made some comments about how, Isaac Newton created the scientific revolution, and he showed how, how religion should be entirely left out of science. It's like, has he read Newton? Like, because Newton, in his books, he talks specifically about God. And it's not even some tangential books. It's within his Principia and his Optics. He talks about God and theology right in the context of his scientific writings. So I think there's a sort of this uneducated view that's sort of a myth about how there are certain scientific figures who kind of led in the new age where we don't have to talk about philosophical or theological issues in science that are just sort of repeated. That's not the case. Yes, there's a question over here.
Yes. I would like to know, how does the Christian belief helping you in your science work and make successful work? And for the new generation, is there the opportunity for them to grow up into a great scientist, just like Newton? Yes.
Okay, so
yes.
So I think I don't believe that being a Christian gives me some edge, okay, in science. Like I don't believe that. I don't think I have some special insight that non-Christians don't have, okay? It doesn't help me in my laboratory do my mathematics better or build my circuits better. It doesn't help in that way, okay? So, but what it does do is it gives me kind of a perspective, and it gives me, I think, an understanding. I have, in my mind, things kind of fit together, I think, in a way that perhaps someone who doesn't have that same perspective, they wouldn't fit together. So I'm kind of interested in history and philosophy and science and theology and sort of trying to see how these things fit together. So at the very least, for me, I think it makes it more fun, okay? Because it's things that I enjoy thinking about. And I think historically people have thought about. So I guess, yeah, I don't think it gives me sort of a technical advantage, right? I think someone who's a Buddhist or someone who's a Hindu can do the science just as well as I can, right? It's not like I've got some edge there. But I am interested, I do think that Christianity provides kind of a worldview that I find very satisfying and compelling. And it's not like it answers all my questions either. It's not like I've got it all sealed up, it's not like that at all. But it gives me a strategy of kind of thinking about things. that's helpful for me. Am I answering your question?
Yeah, thank you.
Sure. Yes, please.
I've certainly read many articles and I've watched documentaries wherein I've seen professors, scientists such as yourself have been ostracized, penalized for holding their views, have not received funding, etc. I know you teach at Wisconsin Lutheran College, so I have to assume that getting hired at Wisconsin Lutheran requires you being a professed Christian. Would that be correct? So you would not experience the kind of reaction that I suspect you might receive at a more secular school.
I think that's fair.
So, in fact, frankly, probably your experience doesn't reflect reality in terms of what you would experience at a more secular school.
Right.
Right? So I just was wondering, when we talk about have you experienced this, have you seen that? Because conceivably, if you were teaching at Yale or Stanford, you might not receive any funding for your lab work as a result of your Christian beliefs, right?
That's possible. Right.
Yeah.
So I don't know for sure.
I think it's true here in Canada.
Okay. Yeah, I don't. So teaching at Wisconsin Lutheran College, it's a Lutheran institution. It's actually the first Christian school I've ever been at. So I went to public schools my whole life. And then I went to a private school that are Cornell University is the decidedly secular Ivy League school. So all the other Ivies actually started as theological seminaries, but Cornell was, from the very beginning, was started as a school that was supposed to be militantly opposed to any kind of theological influences. But nonetheless, you go to a school like Cornell, and there are Christians there. There are a lot of Christians there, right? Different denominations. And some of the faculty are Christians, some aren't, so it's a mix. And it is true that there is, in secular institutions, there are pressures like that probably don't exist at my institution. But there are also, Christians who are committed Christians who do get funding, who are doing research at places like that. And I don't think we should use kind of like sort of a martyr strategy of like, well, I'll never get funding if I'm at a school like that. And it's just because I'm a Christian. Well, maybe I'm just a bad researcher, and that's why. But I don't mean to discount what you're saying. I know that there are these pressures. But I try to downplay that and give people the benefit of the doubt and say, if I'm not getting funding, how could I do it better? What am I doing wrong? And maybe I'm being naive about that. But I think that's probably a better way to approach it than to say, oh, I'm just not getting funding, I'm not getting it because I'm a Christian.
We find, I'm a Welsh Lutheran. I'm not trying to be adversarial, I'm just realistic. One of the things that has always bothered me, being a Welsh Lutheran here in Ottawa, where it's predominantly a Roman Catholic community, is that, in particular, clergy will send their children to parochial schools, religious schools, beginning often at elementary levels, certainly at high school. And I'm thinking, if we are told by Paul and by the apostles to let our light shine, to be salt, I'm somewhat torn by the fact that these young children who are the children of clergy, for example, are not being exposed to what really does exist out in the real world. I maintain it's the role of the parents to bring up their children to have their faith and to value their faith. And I sent my sons to secular schools. Probably one reason was I couldn't afford to send them to a private school, but at the same time I felt they are part of the world. They can witness, they can testify. Although I understand when I look at the school system around me now, I used to be a teacher, I can see so much going on that does bother me. And I can see the reasons for sending your children to a parochial school. But at the same time, if we're all running away from it, how will it ever change?
Yeah, I agree with you. I think there are wildly different opinions on this topic, and people have their own reasons for sending kids to parochial schools and public schools. That's a whole can of worms. That's something we're trying, my wife and I are what are we going to do with our kids for high school? Yes.
It's less philosophical, but it's more
Pardon me?
it's less philosophical, but it's more related to your expertise.
Right.
In terms of the fluids, so in diffusion, molecules move into the diffusion. Do they generate also turbulence? The molecules diffusing have similar pattern or doesn't occur in diffusion?
So you're asking whether, like, when you have molecules that are diffusing through a fluid, do they generate turbulence?
The fluid is stagnant, right?
Right,
There
so-
is no movement.
Right, so it's kind of a question of like what scale you're looking at it at. So, and this is actually a very interesting area of study that researchers are looking at right now. So if you're looking at kind of far back, a fluid, you don't see the atomic or the molecular structure of it. This looks like having a smooth continuum, you might say. But the closer you look up at it, the closer you get up to it, the more you see the molecular structure of it. And if you're trying to sort of capture with your theory that molecular structure, the question is at what scale can you treat something as a fluid, and what scale can you treat it as individual atoms? And you know, there are some equations that describe fluids called Navier-Stokes equations. There's these equations that describe fluids, but a lot of the area of research, people's research right now is, can you develop equations like that for fluids that apply to like granular materials or other like discrete objects like that? So at what scale can you come up with formulas that will describe the motion? Can you take fluid dynamics formulas and apply it to individual small groups of atoms or small groups of grains of sand, for example? I think that's probably the way that I would think about it. So I don't know. That's a strategy I would think about it using. Yeah. Yes.
So, like, I know you're a physicist, and a lot of your examples point to how your controlled experiments are represented within nature. And I see a lot of us in this room are engineers and physicists, but I myself come from biology and a biochemical background. And so some of my courses deal with molecular biology and by designing biological systems. So, for instance, looking at how signals transduce from the surface of the cell to the nucleus and how they change in expression. So, one of my professors says that we can engineer biological systems just like we can engineer a chip. And so that it is not necessarily the engineerability of a biological system which precludes that it must be engineered, but rather that we can engineer it, right? And some of you might have heard the story in China where they tried to do CRISPR on a set of twins. Sadly, one of them is heterozygous, so it's not really perfect. But anyway, the fact that we can change them, there's a quote that says, we spend so much time thinking about if we can do it, we didn't spend enough time asking the question, should we do it? So, like, do you think that between physics and biology, these pointed questions have different weights and are asked differently and are dealt with differently? And like, how do you see how different fields like approach these intersections between theology, philosophy, and the field that they're working in, whether it be biology or physics or engineering?
Right, so you're kind of asking about the ethical aspect of the philosophical ethics applied to biology and to physics. I mean, in physics, the thing that people always talk about, people still wring their hands about for good reasons, is like, nuclear weapons. Like, should we be designing these that are going to be used to kill innocent people? And so these are these ethical questions. That's the one that physicists think about all the time, right? And biologists, I think biologists have a whole slew of ethical questions that they're wrestling with right now. And I'm just, I wish I knew more about biology and biochemistry. I feel like that's a hole in my understanding, So, and, I want to kind of weigh in on ethical things there, but all you do is start talking about CRISPR and this kind of stuff, and I'm lost really quickly, right? So then I feel unqualified to sort of make these ethical judgments, because you get the sense that you need to know all the details in order to say anything about it. And I don't know if that's the way it should be or not. Right? So, because if you really had to know all the details to make ethical conclusions about cloning or whatever, like everyone would have to get a PhD in biochemistry before they vote, right? And that's just implausible. So I don't know how to, how that's best organized or how one can deal with this. I'm having a lot of I don't knows here.
I have a second question.
Right.
So, like, being in the field of biology for so long, I kind of, like, from the public, I get the sense that a lot of people are afraid of GMOs, for instance,
Okay.
right? But like in biology, we make GMOs all the time. When we try to make a mutant cell line, we have to just study how, if you erase this protein, what is the effect? Do you cause a disease, or like does something happen? So these are technically GMOs, and you get to have a more closer relationship with them. And so, do you think by having this close relationship with something that to the public is controversial, it changes how you do things into a bias in another sense, to the opposite?
Yeah, no, I think that is true. I think many times scientists understand the complexities of things, and they tend, in my estimation, scientists tend to be much more reserved in what they claim than by the time it gets to the newspaper. You know, scientists, when they write it in their paper, they'll say, I did this, but I'm really unsure about that, and they qualify every statement. But by the time, it gets to the newspaper, it's like, scientists have cloned this, and and all the nuances are lost, right? So there's a disconnect there between the way scientists are doing things, the way they're talking about it, and the way the newspapers are reporting it. And I think that's a big problem. So, yeah. Yes, I agree.
I'm sure we'll have time afterwards as well to ask some more questions, but I'm going to wrap up.
Thank you.
Huge thank you to Dr. Keane for coming in again today. So just a little bit more about us as well. So we at Illumine, we're a student organization at the University of Ottawa and at Carleton. If you ever want to know more about, what we do, first reach out to our Facebook page. We also have more information. We have flyers here. There we go. About what we do, what we're about. We have movie nights, we have games nights, we have weekly socials, and every social every week we always have like a nice home cooked dinner. And so that's close to University of Ottawa campus as well. And we're also doing a movie night. We're watching Infinity Wars at Carleton University campus on April 5th. So you're all also welcome to that. Great. And last thing too, we also have these forms as well. So if you're interested in feedback as well, we have these forms here. If you want to know more about us, you can send emails regularly to we're up to. And yeah, so again, a huge thank you. And I hope you have a great night.